Hello YouTube! Today we are going to divide and add forces, and that's one of the basic principles of physics. And it does not only apply for force vectors but for all vectors, so you can divide all vectors and add all vectors after you have watched this video. So why do we need this stuff anyway? We need this stuff because we don't know everything. We, for example, don't know what would happen if an object would have this force applied. We may know what happens if the force just goes straight downwards onto the surface here, or if it goes parallel to the surface. But we don't know what happens if it's just this angle. We just don't. Or what would happen if these two forces were to apply on this object? What would happen? We don't know either. Because that would mean it has two accelerations, and that would mean it would go in two different directions at once. That's nonsense. An object can't be at two places at once. But don't worry, there are solutions. There are solutions by dividing and adding forces. In this example, we should divide forces into two directions that we actually know. We know the direction perpendicular to the surface, and we know the direction parallel to the surface, and what happens with the object if a force is applied in that direction. And we also know what happens if we add those two forces up here, and we get a sum of those forces, and we know what happens with that sum, because that's only one acceleration. We know in which direction this object is going to move, in this purple direction. So let us start with adding forces. Adding forces is actually quite simple. To add two forces together, we only need to move one of the forces in its base and move it towards the head of the other force. So we take this force, for example, and just pull it over here, and then we put it on top of the other force, on the arrowhead of the other force. And then we get this force, which is nice. And this is our final force. From the base of our first force to the top of the second force, that's our final force. So this line right here. But we could also do it another way. We could also move this force, this lower force right here. And if we did that, we would move it up here, and it would go here. And physicists saw a very, very important principle here. We have moved both forces parallel, so we get a parallelogram, aka a rhomboid. So with this thing, we can actually create these final added forces quite easily. We just need to draw parallels. So this line here, we draw a parallel on top of the other line, on top of the other vector. So we draw a parallel to this lower vector on top of the other vector. And we do that again for this vector right here. We draw a parallel to this vector right on top of the other vector. And if we do that two times, we get an intersection of both lines. And where those both lines intersect, that's our arrowhead of our final added force. And that's actually quite easy. We just need to draw parallels, nothing more. So to add two forces together is actually the simplest thing there is. We just draw parallels, nothing more, nothing less. Let's try that again with this thing right over here. And we just try it again, and we see, oh, this parallel is about this line right here, and this parallel is about, let's see, about this line right here, and we get the final force, which is just about this line right over here. Now there's one, or let me say two cases where this doesn't work, which are these two cases on the right here, where they are either anti-parallel or parallel to each other. When the forces are anti-parallel or parallel to each other, you can't draw the rhomboid, you can't draw the parallelogram. What you then have to do is use the method we discussed first. You put the arrowhead of the one to the head of the other, and blah and blah. And for example, for this case, you just move this vector down here onto this one. And if they are the equal length, it would result in a null vector. There's no vector right here. There's no result vector. If one of them was larger, let's say the upper one was larger, there's going to be slightly a slight vector going upwards. If the lower one was larger, the vector would go slightly downwards. So our final vector, for example, can look slightly upwards or slightly downwards. So what you actually just have to do is subtract both forces, or the length of both forces. If we have them parallel to each other, we just have to add them. So for example, in this case, we would get this longer vector by just adding those two forces, which is in the end just putting the one force on top of the other force. So it would be like this. So we put this force up here. So now we know how to add forces if they are parallel, anti-parallel, and in any other angle to each other. If they're parallel or anti-parallel, we subtract or add them. And if they're at any other angle, we use our parallelograms or our rhomboids. Now the second step for physicists is dividing forces. Dividing forces is also quite important. And you need to have directions in which you want to divide the force actually. In my example up here, we actually knew two directions. We knew that we wanted a parallel direction and a perpendicular direction, or an orthogonal direction. So parallel and perpendicular, those are two directions. So we can apply them once again. So look at this example right here. Right here we also have a direction parallel and perpendicular to something. And now to get both components of this force, one that is parallel, one that is perpendicular, we just draw the parallelogram once again. We use this line and draw it parallel to this other line, and it has to intersect at this head right here. And we use this line, draw parallel to it, and it has to once again intersect at this head. Because if it intersects at this head, if we use the components, the parallelogram is actually going to reach this point once again if we add the components together. So this is our first component, and this right here is our second component. If we add these components, we get the same parallelogram once again, and the red force is going to be the result of those two components. So let's do it again. We take some random force, some random directions, and we just draw parallels. So we need a parallel that goes down like this, that's better, or like that, and one that goes straight up to the right, about this, or let's draw it a little bit steeper, like this. And our components are the forces going along these axes until we meet the intersection. So the intersection is always going to be the head of our force. And remember, this is a parallelogram, so this force should be equal length to this force right here. Okay, let's move to another example, a little bit harder, this one, which is we have a circular movement, we have a rotation, and the force is actually not pointing directly towards the middle of the rotation, but to some other arbitrary point. How do we do this? Well, one could think that drawing a parallel would mean that we also have to draw this round line here, but that's complete nonsense. We actually, right now, want to have the tangent of the circular movement. We actually want to have the tangent of the circle and the line perpendicular to the tangent. Those are our two directions, and we get one component of this force, which is going to show which is going to be in the direction of our tangent, and one that's going to be in the direction of our perpendicular line. So these are the two parallels, and this is our first component, which is parallel to our tangent, and this is our second component, which is parallel to this perpendicular line. Now we have successfully split this red force up into two parts. One part that's going to keep the object in its circular movement, and the other one that's going to accelerate it along this circular movement. Okay, now let's get a little bit harder, because that's all quite easy. We know how to divide forces by drawing parallelograms. We know how to add forces by drawing parallelograms. So let's try it a little bit more difficult. Right now we want to add 3 or 4 or more forces, and that's actually quite simple once again. All you have to do is add one force to a second, and then add the result to the third, and add the result to the fourth, and add the result to the fifth, and so on. So for example, we have these forces right here, and we take the result of the addition of this left force and these two forces, and that's about, let me see, about this line. And then we just take the result and add it to our last force, and that would be about, this is a parallel, yeah, this is a parallel, and this is a parallel. Then we have our final parallelogram, and this force is going to be the final force. So this pink force right here is our final force. we just added the two red forces right here, and we took the result and the last force to add them together to get our final force. So we always get the result of two additions, and then we take the result and add another one, and we take the result and add another one, and we take the result and add another one, and so on. For four forces that takes a little bit longer, but it's also quite okay. So for example, I add these two right together, that's this parallelogram and this final force, and then I do it another time, so we have these two forces. So this is the parallelogram, yeah, the parallelogram, and we have these two forces, and then we have to add these two together. So that's going to be our final parallelogram. I'm going to draw it in another color because otherwise it's going to look quite crappy. So let me see, about this, and this is going to be our final force, which just happens to be in this direction. So we take forces and add them and add them and add them, and once again we completely don't care which forces we take first, because it doesn't matter which forces we take first. If we move this force, it doesn't matter, or if we move this force, it doesn't matter. So we can actually move whatever force we desire. It doesn't matter. So we can start the parallelogram thingy with whatever force we want. We can start with this and this, or this and this, and these and whatever. Doesn't matter. So now there's one more thing. An interesting part to adding forces together is that you can also add their components. It doesn't matter if you add the forces directly or if you add their components. For example, right here, if we would just add them directly, we would get here the parallelogram is about, let's see, about this one, and the added force is this green one right here. And let's see what happens if we divide them into components first. So we take, this is going to be my one axis, and this is going to be my second axis, and you might see why I chose these axes. And then we draw our parallelograms again, so parallel to this into the head of this, and these and this. So these are our parallelograms. We have this line here, which is parallel to this line which is parallel to this one, and for the right force we have these two again, and this one and this one. So we once again just add the components. So we get this component to the left and this component down for the left one, and we get this component to the right for the right one, and of course don't forget the other component downwards for the right one. So if we add these two components together, they had equal length. Now I could prove this for hours, but let's just assume they're for equal length, and that means they cancel out. And what's left is these two forces going downwards, and these two forces going downwards add up to our green force from the parallelogram. Usually you don't even need this, because it's much more complicated than just drawing the parallelogram. You see, drawing the parallelogram was quite easy. We drew two lines, and then we had our result. And here we had to draw 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. So that's quite more difficult. We don't actually really need. But it's a neat little trick, and it's going to help us understand that it doesn't matter if we take the components or the actual force. There are two different ways to describe the same thing. If we describe all three of these forces, doesn't matter, we could also describe just the one big result. They're the same. It's like saying 2 plus 2, which is these forces added together, is 4, which is the result. Both are the same, just two different representations. The same goes for the components. Component A plus component B is equal to C, which is the final force. Two representations for the same thing. Now where do we need such things? For example, on such an incline right here, we actually just know what happens if there's a force parallel to this incline, and we know what happens if there's a force perpendicular to this incline. So we actually have to divide this force of gravity, into two parts, which is just by drawing the parallels. So this is the parallel to this line, this is the parallel to the other line, and we get the two components, which is just along this line we go until we get to the intersection, and along this line we go until we get to the intersection. So right here we have the two components. Now we know what happens to this object. With this one force, it's going to get pressed against the incline, and with this other force, it's going to move downwards. Another example is the Wien filter. There's going to be an electric force going upwards for all electrons flying through it, and the Lorentz force is going to pull them downwards. And if both forces are at equal length, the resulting force is, as we saw, is cancelling each other out, and it's zero. Now another example is, for example, the electric field lines between a positive and a negative charge. We get them by taking infinitely small positive charges and just testing where the force would lead them. For example, these two positive forces would repel each other, so that would be a repellent force, and the positive force and the negative force are going to attract each other, so that's going to be an attracting force, and we want to know where it actually goes. And where does it go? Well, it goes in the direction of the addition of both forces. So we just take the addition of both forces, which is about this line, and once again I did that in my head by just adding the parallels. So this parallel, and you see that was about right. So by that, and by repeating that step again and again, we actually get the resulting line, which looks about like this, and I guess you have already seen those pictures again and again and again, and they're probably getting quite boring, but it looks about like this, just about. And we do that by simply placing this positive charge at any position we desire, and looking what the added force of the negative attraction and the positive repulsion is. So let's now look at another example. This one is quite interesting because it's actually telling us one important fact. This right here is a velocity vector, our initial velocity vector from falling and throwing, but we can actually see that we can divide it into its components because it's a vector, and what we learned applies for all vectors, not only forces. So if you take the initial velocity vector from our multidimensional throwing, we actually get this line right here, which is parallel to our y-axis, and this line right here, let's draw them like that, which is parallel to our x-axis. And when we take these when we follow the axis until we get to our intersections, we actually get the two components, which is this component and this component. And in the last video, I just threw around that they are the sine and cosine. This time we can prove it, because the angle between the x and y axis is 90 degrees. The angle right here has also been 90 degrees because it's a parallelogram, so this is a rectangle actually, which is just a special parallelogram. And if we take this angle right here, which is our angle phi or theta or whatever you want, and now you take the opposite leg and divide it through the hypotenuse, you actually get the sine. So the sine is nothing else but this opposite leg divided through the hypotenuse. So what's this opposite leg? Well, it's the same as this one, because it's a rhomboid or rectangle, however you want to look at it, which is just our velocity in the y direction, and we divide it by our total velocity. And that's where I got the formula from for our velocity in the y direction, which was just sine of theta times our initial velocity. Same goes for our initial velocity in the x direction. We just take the adjacent leg. The adjacent leg goes with the cosine. Cosine is just Vx divided through V, and we get Vx is equal to cosine of this angle times our total V. Okay, I really hope you got that all. So we add forces by drawing parallelograms, and if we can't do that, if they're parallel or anti-parallel, we just add when they're parallel and we subtract if they're anti-parallel. To divide forces, we also draw parallelograms with the two given directions in which we want to divide the force into. And finally, we add multiple forces by just adding two forces and then taking the result and adding the third and taking the result and adding the force and so on. And we can actually add forces by adding the components. That's just neat little trick. And I hope you enjoyed the video. I hope we are going to see each other next time. And goodbye. See you.